to where we started. Just evaluate this in a little different way. All right, I want to move on now to what happens. I mean, so far what we have considered here is that these capacitors between the plates is a vacuum. Our air is pretty close to that in terms of. I mean, unless you get to very, very high voltages, of course, and air then becomes a conductor, as we talked about before. But assuming here up to this point that between the plates is it's something that really doesn't play a role or interfere with the how a capacitor works. I mean, you can think of this as like a stage that doesn't really interact with the actors. But if we were to place a dielectric material in between, then the stage begins to interact with the actors in this case. And the actors being the capacitors are the plates. Now, I was wanting to show this, but didn't really have time. Unfortunately, our lab manager has retired. I guess I'm now the lab manager. But yeah, I mean, this is a pretty cool thing to show that, if you were to, let's say you were to charge up a capacitor and you connect it to electrometer, this just measures the potential across the plate. There's a very large impedance between two. There's just almost no charge transfer across this electrometer. And so to worry about this being a leaky capacitor as a result of including this. So, all right, so you have a voltage that you start out with that you're measuring, and you have a certain amount of charge as a result of having this initially charged connected to a power supply, albeit a wall power supply, or it could be a battery for that matter. And then you disconnected the battery, and so now you have these charges. These charges are isolated. They can't go anywhere. We have charge conservation. And so when we insert a sheet of dielectric, it could be anything that's not a conductor for that matter, but for instance, a polyethylene glass, plexiglass, like that's what I have here. If I was going to do this, I was going to use a piece of plexi. But what happens when you insert this into between the parallel plates? So you see the voltage will go down. The charge will not. The charge on the plates will stay constant. It has no place to go. The fact that you have just reduced the voltage, you're like increasing the capacitance. And so if you were to have this connected still to a power supply, when you inserted this piece of dielectric, well, the power supply would have to do work. You would have to put more charge onto these plates to bring it back up to the voltage that you have it, at least the power supply set at. Remember, most power supplies provide a constant voltage or a constant potential. And so what would happen, it would then begin to transfer charge from the power supply onto the plates to bring the voltage back up. But in doing so, the amount of charge goes up. And so basically now you have a more efficient capacitor as a result of doing this. I'll explain a little bit what happens or why this happens. So when a piece of dielectric is inserted between the plates of the capacitor, well, the electric field, it decreases. And this is a result of polarization, the charge within a dielectric. All materials in some ways are prone to being a dipole, whether it's induced or whether it's it's naturally occurring. For instance, water is a naturally occurring molecule that's it's a dipole. Now, thinking of water, of course, I mean, all the dipoles are just kind of randomly oriented. I mean, it doesn't really have any direction. Until you apply a electric field, then all these dipoles will begin to line up in that direction, such that it lines up the direction of the electric field. And these induced charges are a result of these dipoles that you can see here on the far right. And this I'm going to call it induced charges. And we'll talk a little bit more. I think we have, well, we got time. You're doing good for time today. So I'm talking fast. Hopefully not too fast for you guys. So, as I already mentioned, some molecules, such as water, NHO, N2O, or CH2, for example, they form they're natural electric dipoles. And molecules, sometimes is, I guess the standard term is a polar molecule. And, when there's no electric field present in the gas liquid or, whatever it is, it doesn't have to be a solid, like most cases it is. The molecules are oriented. They're just randomly oriented. Maybe not so much for even in a solid. I think that's the case as well. So what happens when you apply electric field? Well, they tend to orient themselves such that the positive side of the dipole is in the direction, it wants to go toward the direction of the electric field. The negative side wants to go in the opposite. So they may not be perfectly aligned, but they're more aligned than what they were prior to the electric field being applied in this case. Even some cases that some molecule may not naturally be a polar molecule will be affected by electric field. It will become more dipole-like. It may not be has a strong dipole moment as that, such as water, for instance, which is actually a pretty strong one. But it's just a result that the positive charged nuclei in the molecules will move in a direction of the field, and it pushes the negative charges in the opposite direction in this case. So it doesn't really necessarily have to be a very strong dielectric. I mean, maybe in some cases you want to fill a capacitor with something that's not as efficient as it would be if it was something like the polyethylene, for example.
So a more random electrical field results in a more efficient capacitor?
Oh, a random field? You mean as a result of the dipoles in the dielectric between the plates being random?
Yeah, something like that.
Yeah, I mean, if there's voltage is not applied across the capacitor, actually it's just neutral in that case. It's really not functioning. And if the dipoles are just kind of random, as you stated out, it really doesn't hurt anything or doesn't really affect anything. It's only till you begin to apply a voltage across the capacitor that charge builds up on the plates, and as a result of these charges, you get electric field. And the electric field orients these dipoles in such a way I've just described. And direction of the electric field is the side where the positive part of the molecules will orient itself, and opposite for negative. So I mean, it's just like it's almost like starting an engine. It really doesn't do anything until you apply a voltage, and the capacitor doesn't really do. I mean, it doesn't really. Yeah, I mean, it doesn't really function if it's not powered, I guess is what I'm trying to get at. Did I answer your question?
Somewhat, yeah, that's fine. Thank you.
Well, maybe if the next few slides will help clear that up. I don't know. Let's see. So, like, here's a case here. You have a piece of dielectric, and it's immersed in a uniform electric field. And you can see what happened here is that they orient themselves, such on one side you have a negative charge density, surface density, what we call sigma I. And then on the other side, toward on the direction of the electric field, you have a positive side. And of course, what would happen if you turn the electric field off, then these dipoles would just rotate back to their natural state. It's only in the presence of electric field they'll begin to line up such that you'll have this transfer. I guess one of the charges are just starting to accumulate as a result of them feeling this electric field. The electric field is actually doing some work to reorient the orientation, or just orient the angle of the dipoles. I don't know, it's just kind of a sequence. Okay, now you have a parallel plate capacitor, say it's a vacuum inside or just air. You have sigma is defines as your is the charge density on the plates. Negative sigma is on the right hand side. And as a result of this, you have an electric field, so it's called E sub naught. So let's just quickly insert the dielectric before it can respond. So now you have these electric fields that are just passing through the dielectric, as we show here. Say maybe it takes a few nanoseconds for it to respond. So we took, say it took us less than a nanosecond to put in the dielectric. It'd be a challenge for some of you. But what will happen here is the following. You said as a result, we talked about earlier, these dipoles will set up or these charges on the surface of the dielectric, somewhat canceling out the charge, at least near the surface. I mean, it doesn't really cancel out. But if you use Gauss's law and determine what the electric field is, the combination of these charges, and near the surface, you'll get a weaker electric field as a result of this. It's only because of these the dipoles in this material are oriented in the way that it cancels out, or it just, you can think of two ways. It's a surface charge that's built up, surface charge on the dielectric, not on the conductor, just near the conductor, but not. I mean, it's just, you can say it's in contact, but there's no charge exchange between the conductor and the dielectric. So just make sure that's clear. Ready? Now, you've probably seen me do this already too. I mean, if you have like a neutral sphere, it's not a conducting sphere, it's a dielectric, and it's basically what happens. It becomes polarized, and it's attracted to the Van de Graaff as a result of it being polarized from the electric field emanating outward from the Van de Graaff. So regardless, whether the Van de Graaff is negative or positive, it will always be attractive as a result of the dipoles in this material rotating in a way that will give you this this effect that we're seeing. So it's always attractive. So I'm going to summarize a bit. We're about to run out of time, but so when insulating materials inserted between the plates of the capacitors, whose original capacitance is say a C naught, the new capacitance is greater by a factor of K. This is something we're defining now, the physical thing. Where K is the dielectric constant of the material, whatever that might be, whether it's water, polyethylene, plexiglass. This is kind of way to look at it. I mean, you have your new effective or equivalent capacitor, and C naught is the capacitance in a vacuum, no dielectric. And this big K is the dielectric constant. Okay. So substituting C naught for like a parallel plate capacitor, we have epsilon naught times the area of the plate divided by the distance between the plate. And remember this this is permeability of permittivity of in a vacuum. It doesn't necessarily have to be that. I mean, you could write this permeability, permittivity in terms of what inside a particular dielectric, and it's basically this K value times epsilon naught. Epsilon, you know, also, obviously, we know that this will affect the energy density as well. We're running out of time, so what I want to do is just, I mean, I think this is kind of obvious. This, I think we already looked at it as 1/2 CV squared is relationship for energy inside a capacitor when it's charged. But there's just some examples here. I mean, for a vacuum, obviously it's one. You know, air is very close. You know, in Teflon, not so great, but it's better than air. Mylar glass, but it turns out, you know, water is like one of the better dielectrics, although it's not the most practical one to use, and you know, and encapsulated inside a capacitor, especially if you want it rated below 0 C. It's not going to quite work. Yeah, such is life. But anyhow, I guess that's all I have for today. I'll stick around for questions. If you guys have any?
Yeah, I'm a little confused. So I understand that capacitance is impersonal is impersonally related to voltage.
Yeah.
But why is capacitance also, because voltage equals the electric field,